In this video, we're going to continue talking about AC analysis and the concept of impedance as the ratio of voltage to current in an AC situation. And just as a reminder of the assumptions we've made for AC analysis, we've assumed that all of our signals are of the form of some kind of a sinusoid, like that. Cosine is the typical one we pick, cosine omega t plus some offset angle. And we're also going to use Euler's equation, which says we can decompose our cosine into two complex exponentials. So one of the complex exponentials is e to the plus j omega t plus phi, and the j multiplies both of them, plus e to the minus j omega t plus phi. And when we use Euler's theorem, what we do is we love putting these things through differential equations. So we track each of these one at a time through our circuits. And typically what I'll focus on is the plus term, but the minus term, all the math is the same except there's that one little minus sign. And so when we made up the concept of impedance, we assumed that V or I was of this form, this complex exponential. And that made, when we put that through our components, we came up with the idea of impedance. And as a review, for a resistor, the impedance of a resistor turned out to be just R. That's the ratio of V to I in a resistor. And for an inductor, we decided Z of an inductor was equal to J omega L. And finally, for a capacitor of value C, ZC equals 1 over J omega C. So those are the three impedances of our three favorite passive components. And the units of these, the units are in ohms. R is measured in ohms. That's the normal Ohm's law. And we use the same units for impedance of inductors and capacitors. So this is in ohms and this is in ohms. That may seem a little funny that because there's this frequency term in here, but this is what it is. So in the rest of this video, I want to qualitatively look at the value of these impedances and specifically look at what happens when there's a range of values of the omega term. What happens at zero frequency and low frequency and high frequency and infinite frequency. So let's go ahead and do that. So we're going to look at the impedance terms at different frequencies, and we'll measure frequency as radian frequency in this. So let's talk about zero frequency, and we'll talk about low frequency. These are qualitative boundaries. We'll talk about high frequency, and let's talk about infinite frequency. So we're going to build a little chart here. All right, so these are the value of omega here. And now we'll do our components. First we'll do our resistor, and we're going to fill in the table for ZR. And we know that equals R. So at any frequency, R is just R. Couldn't be simpler. At zero frequency, which is just called DC or a battery, R is R. At any low frequency, R is R, R is R. At infinite frequency. So there's no dependence on frequency in R. So now let's do the inductor. And we decided that Z of an inductor was J omega L. And let me do something very specific. I'm going to get rid of this J. I'm going to basically say I want to just look at the magnitude of the impedance. If we just look at the magnitudes, the magnitude of Z inductor is omega L. So now let's fill our table in for omega L. So when omega is 0, the magnitude of the impedance is 0 for an inductor. And when the frequency is low, when omega is low, the impedance is going to be relatively low. And as the frequency gets high, Then omega L becomes a larger number, so it becomes high. And if we let the frequency go to infinity, then omega becomes infinity, and this becomes infinity. So we see in an inductor, from low frequency to high frequency, the impedance of the inductor goes from 0 up to infinity. All right, let's fill in the last one here. Here's our capacitor. And the Z of a capacitor equals 1 over j omega c. And the magnitude of the impedance is just 1 over omega c. All right, so let's plot that out. What is 1 over omega c when omega is 0? Well, it's infinity. And what if omega is a small number? If omega is a small number, then this is a large number. This is a high number. And if the frequency gets very high, the higher omega gets, the smaller the magnitude of Z gets. So we get low here. You see it's anti-symmetric with the inductor. And finally, if we let the frequency go to infinity, 1 over infinity times C is what? Is 0. With this chart, I can show you some of the words that we use, some of the sort of slang words or jargon words that we use in electrical engineering to describe the behavior of L and C at different frequencies. So as we said, R is R at any frequency. So resistance is constant. In inductor, it changes over frequency, over this big range of frequency. And at 0 frequency or low frequencies, the impedance is very low. So this leads to the expression we say an inductor looks like a short. An inductor looks like a short at low frequency, at 0 frequency or low frequency. And now let's go to high frequency. The impedance gets high and it eventually goes to infinity. That's the impedance of an open circuit. So we say L equals an open at high F, high frequency. And it's a short at low frequency. Let's do the same sort of jargon investigation here for our capacitor. A capacitor at 0 frequency has an infinite impedance. So it looks like what? It looks like an open at low frequency. So let's go look over at high frequencies. High frequencies, the impedance becomes very low. And at infinite frequency, it becomes 0. And that's the impedance of a perfect short. So the expression, the slang expression you'll hear is that a capacitor is a short circuit at high frequency. So the reason I'm telling you about this, very often experienced engineers will talk to beginners and use these kind of terms that, oh, an inductor looks like a short at low frequency. And I wanted to show you where these things come from, where these terms come from and what they mean. And this is not a simple idea. You saw how many assumptions we made and how much work we did to get to this idea of these sort of common or familiar expressions for how our components work. I hope that helped for you to see how this comes about.